In this lecture, we discuss about the operators in quantum mechanics. This part we split into two lectures. In the first part, we discuss few operators in the quantum mechanics and remaining one in the second part of the lecture. Now here we see what is an operator. Operator is a basically mathematical rule. We know every mathematical operation like addition, subtraction, multiplication, dividing, integration, differentiation of one variable. These are represented by a characteristic symbol. That symbol is an operator. Here, when such an operator operates on a function, then it changes into new function and it gives the definition. That definition is operator is a mathematical rule of the operation which changes a function into another function. That is operator A. A is denoted by hat or cap. A cap or A hat f of x equal to g of x. For example, if A operator is a differential operator, that is d by dx, and function f of x we choose as a x square, then what is the result you get? D by dx of x square is equal to 2x. Hence, here initial function is x square. After operation of the differential operator, it gives function 2x. Such a rule is general rule in the mathematics. But in the quantum mechanics, when operator which operate on a well-behaved function f of x, then it reproduces the same function multiplied by constant factor a. That is, operator O which operate on a well-behaved function f of x equal to a f of x. Here we write the function sin x and the operator is d square by dx square. Then what it gives here? Initially we differentiate d by dx of sin x is cos x. Again we differentiate the same term, then cos x is again sin x. Hence it reproduces the same function multiplied by constant factor a. Hence O is an operator. F of x is a well-behaved function. When it reproduces the same function, that function is known as eigenfunction of an operator, and the constant a is known as eigenvalue operator. Using such operators, we use in quantum mechanics. All operators must satisfy the eigenvalue equation. These operators are position operator denoted by the symbol x hat or cap. Similarly, y component position and z component positions are denoted by y hat or z hat. Linear momentum operator in one dimension, px hat, py hat or pz hat, and we extend it into the 3 dimension. Total energy operator denoted by the symbol E hat or E cap. Kinetic energy operator K hat. Hamiltonian operator denoted by the symbol H hat. Parity operator denoted by the symbol pi hat, and angular momentum operator in one dimension Lx, Ly, and Lz, and extend it into the three dimension. Now, how the operators in the quantum mechanics are constructed. First operator we choose, position operator. Position operator is denoted by symbol x hat. Now we choose here the position of a particle that is represented by its coordinate x. Therefore, the x position of the particle, we choose an operator which operates on a well-behaved function. Then the result is as it is, it doesn't change. Position remains same, function remains same. Therefore, the position of the particle is itself its operator, and therefore in the operator form the equation is represented as A x hat equal to x, since position operator is itself its operator. Second, linear momentum operator denoted by px hat, one dimension. X component of linear momentum operator is px hat, similarly y and z, py hat, pz hat. We extend in one dimension into three dimension. Now, how we construct linear momentum operator? For that, we choose a wave function for free particle moving in positive x direction is represented as psi of xt is equal to a into exponential I kx minus omega t. Now, what is the k and omega? K is the propagation vector along x direction and omega angular frequency. Hence, firstly we express k and omega in terms of x component momentum and energy. That conversion term we discussed earlier and we write directly here. K replaced by px by h cross and omega replaced by e by h cross. Therefore, this exponential term becomes a into exponential I by h cross px into x minus e into t, and say this is the equation number 1. Now we differentiate psi term with respect to x if we find the linear momentum operator in the one dimension. Hence, differentiation of psi with respect to x gives, here we differentiate equation 1 with respect to x, we get da by psi by da by x is equal to a into I by h cross px into exponential I by h cross into pxx minus e into t. Again, a into exponential term is psi. Therefore, we write I by h cross px psi. Again, simplifying I by h cross directly we take on the other side. Equation becomes h cross by I da by psi by da by x. Now, h cross by I we replace by minus I h cross, since if we multiply to the numerator and denominator by I, denominator is I square, it is minus sign, minus numerator is as it is, minus I h cross da by psi by da by x is equal to px psi. Therefore, we write the eigenvalue equation minus I h cross da by psi by da by x is equal to px psi. That equation 2 is an eigenvalue equation for the linear momentum, x component, linear momentum. In that equation, what is minus IH cross dev of dev by x? It is a differential operator. What is psi and px? Px is an eigenvalue and psi is an eigenfunction of the operator. Hence, minus IH cross dev of dev by x is called as linear momentum operator and it is denoted as px hat. Therefore, px hat is equal to minus IH cross dev of dev by x. This is the x component linear momentum operator. Similarly, y and z component, we write py hat equal to minus IH cross dev of dev of y and z component linear momentum operator pz hat equal to minus IH cross dev of dev of z. In the 3 dimension, we write linear momentum in the 3 dimension p hat equal to I px plus jpy plus k pz. Now you know px is minus IH cross dev of dev by x, py is minus IH cross dev of dev by y, and pz is minus IH cross dev of dev by z. Therefore, minus IH cross we take outside and we write in the bracket I dev of dev by x plus j dev of dev by y plus k dev of dev by z. This term is replaced by a del operator and the value we write minus IH cross del, that minus IH cross again replaced by in plus sign h cross by I multiplied to the numerator and denominator by I, we get h cross by I del. Hence, P is an 3-dimensional linear momentum operator and its value is h cross by I del. This equation B represents linear momentum operator. Now we see total energy operator in terms of differential with respect to time t. Now how we find total energy operator in terms of the differential? Again we use equation, here is 2, and differentiate with respect to time t. Equation 1 you know, psi of xt is equal to a into exponential I by h cross into bracket pxx minus e into t. That differentiate with respect to t here. Delta psi by delta t is equal to a into, with coefficient of t minus I by h cross into e into exponential is as it is. A into exponential is psi. Hence, minus I h cross into e psi. Again, this minus I by h cross we take on the other side and we write the equation minus h cross by I delta psi by delta t is equal to IH cross delta psi by delta t. Since this term we simplify, again multiplying to the numerator and denominator by I, we get IH cross delta psi by delta t and that equal to E psi. Hence, the eigenvalue equation we write IH cross delta psi by delta t is equal to E psi is an eigenvalue equation for total energy operator. Again, we see IH cross delta of delta t is an differential operator. E is an eigenvalue of the operator and psi is an eigenfunction of a given operator. And therefore, IH cross delta of delta t is an total energy operator denoted as E hat equal to IH cross delta of delta t, and that equation we see equation number C. Nextly, we find kinetic energy operator. Kinetic energy operator denoted by the symbol K hat. Now, how we find the kinetic energy operator? For that, we start from momentum operator that we define earlier, minus I h cross del by psi by del by x, or h cross by I del by psi by del by x, that equal to px psi. Here, this equation we again differentiate with respect to x. Then what is the result? H cross by I del by x of del by psi by del by x equal to px del by psi by del by x. Now, what is del by psi by del by x? That value you know, del by psi by del by x is equal to I by h cross px psi. Hence, that value we write here, I by h cross px psi, and that value del by psi by del by x we substitute here. Therefore, we get h cross by I del by x of del by psi by del by x is equal to del by 2 psi by del by x square equal to, here del by psi by del by x is I by h cross px psi. Therefore, we substitute here px I by h cross px psi. Therefore, the result is h cross by I del by 2 psi by del by x square is equal to px into I by h cross px psi. Therefore, the value is px square psi into I by h cross. This way, I by h cross again take on the other side. And we write the h cross square by I square into del by 2 psi by del by x square is equal to px square psi. Again, here the I square is minus. Therefore, minus h cross square del by 2 psi by del by x square is equal to px square psi. We find the kinetic energy operator. Therefore, we divide by 2m on both sides so as to get the kinetic energy term. Therefore, minus h cross square by 2m into del by 2 psi by del by x square is equal to px square by 2m psi, and px square by 2m is the kinetic energy. Hence, in terms of the kinetic energy symbol, we write k psi. Here, minus h cross square by 2m del by square by del by x square is a differential operator which operates on the function psi. It produces the same function psi multiplied by constant term k, and that k is an eigenvalue of a operator. Hence, the kinetic energy operator minus h cross square by 2m del by square by del by x square is denoted by the symbol k hat, and it is k hat is equal to minus h cross square by 2m into del by square by del by x square. And that equation we write in 3 dimension as, only we replace del by square by del by x square in the del square, that k equal to minus h cross square by 2m into del square. This is the 3-dimensional kinetic energy operator denoted by the equation D.